In this video, our question is, how do we draw free body diagrams? Whenever solving force problems, we want to draw a picture representing all the forces acting on an object, and it will help us to analyze and solve the problem. We call this picture a free body diagram. Now, how do we know what forces are acting on an object, and so therefore know which forces to draw in our picture? Well, the gravitational force is almost always present. In this class, we will always be solving problems where we're on the Earth, and so we'll always have that gravitational force. And gravity always pulls straight down. So we'll always draw in the gravitational force, and we'll draw that force straight down. Then we'll ask ourselves some questions. First, if there is a surface, then we will either have a normal force, which is perpendicular to the surface, frictional force, either static or kinetic, which is parallel to the surface and opposite the motion, or both. If there is a string, rope, cable, or something of those sorts, then there will also be a tension force present. Any other force that doesn't fit into those categories, gravitation, normal, friction, or tension, we are going to label those as applied forces. And those are the types of forces that will be given to you. Those would typically be forces like a person pulling a wagon, or something from like a dog pulling a sled. If we have a sled race. So let's practice a few of these to show you what I mean. The first one that we're going to do is a person sitting in a desk. So if we have a person sitting in a desk, first we have to draw the person. Now, physicists, myself included, are typically not your best artists. So we're going to keep these pictures as simple as possible. So here's a picture of a person sitting at a desk. There we go. It's just a dot. All of our force diagrams are simply going to be just a dot being drawn as the object. It makes it a lot simpler. And so now we have a person sitting at a desk. So we go through our notes here. We go down the line. The first thing we always do is we draw in gravity. So gravity is straight down. I draw the arrow. And I also label that force, Fg. Remember, all forces are F. We simply give a subscript to designate which type of force it is. Then I ask, is there a surface? And yes, there is a surface, because the chair is considered a surface. You're sitting on the chair. So therefore, there's a normal force, and that is perpendicular to the surface. So the surface is horizontal. Therefore, the normal force is going to be upward, and I'll label it as Fn. Now notice here how I drew my normal force the same length as my gravitational force. I want to draw these lines, these arrows represent the force vectors, and I want to draw them proportional to each other. So because the normal force is balancing out the gravitational force, it will be the same size as my gravitational force. Now, although there is a surface, there is no friction present in this situation, because we have no tendency to slide off the chair. The chair is not inclined. We go down the line. Next is the tension force. There is no rope, string, or cable, so there's no tension. And there's no person or animal or anything like that pushing on the person either, so there's no applied force. And so this is our end product. Here's our free body diagram. The next picture, the next free body diagram, we have a picture frame that hangs by two strings that make a 100-degree angle with each other. So we draw our picture. There's our Mona Lisa right there. There's our dot. We draw our forces. The first force we always draw in is the gravitational force. That is always straight down. So no matter what, we always have that straight down force, the gravitational force. Next thing we do is we ask, is there a surface? And there is not. In this case, it is hung by two strings. There is no surface that it's resting on. So there is no normal force. There is no frictional force. Next thing we look at, is there a tension force? And yes, there are two strings. Those strings make a 100-degree angle with each other. I'll label them both as Ft because they are tension forces. And it's always good if you can to write in the angles that are given. That'll help us out later on. So it's a 100-degree angle between the two strings. The tension force, by the way, is always along the line of the string itself. There is no applied force. There's no person or animal or anything like that pushing it, so we're all done. The third force, the third free body diagram, we have a car that accelerates as it drives forward. So we draw our car. There's our Lamborghini there. We go through our forces. First thing we always do is draw the normal force. I'm sorry, draw the gravitational force. Gravitational force is always straight down. Then we ask, is there a surface? And yes, there is a surface. The car is driving on a road. The road is level, we're going to assume. And so therefore, the force, the normal force, is straight up. It's going to balance out that gravitational force, so I want to draw it the same size as the gravitational force. Next we look at, is there any friction because there's a surface? And yes, if you were to take your foot off the accelerator, the car would slow down, so there is friction. And if the car is, I'm going to say the car is moving to the right. Okay, so I'm going to draw my car here. My car is moving to the right. So the friction opposes that motion. If the motion is to the right, then the friction is to the left. The car is moving, so I'm going to label this as the kinetic friction. So I have two choices when I write down my friction. Is it kinetic or is it static? There's no string, rope, or cable pulling on the car, so there's no tension force. But there is an applied force this time, and it's the engine propelling the car forward. And so it's going to be a forward force, and since it accelerates forward, I'm going to draw that applied force longer than my frictional force because it accelerates forward. So there's my free body diagram. I have four forces that time. What I'd like you to do is I'd like you to pause the video at this time and try drawing these three free body diagrams. When you're done, unpause the video and see how well you did. Okay, welcome back. The first one we have here is a falling paratrooper in the presence of air resistance. So we draw our paratrooper. There he is. First force we always draw in is the gravitational force. That is straight down. We label it as Fg for gravity. Next, there is no surface. We're in the air. So there is no normal force. There is not a friction at all. There's no strings, ropes, or cables in this situation. And so there is no tension force. But there is an applied force from the air. And that force is then going to oppose the motion. So in a way, it is a type of friction. But I'm going to label it as an applied force. There is some wiggle room here if you apply it as a frictional force because it opposes the motion. That is acceptable. But I'm going to label this as an applied force, and it is upward. It is opposing the motion. The next one, it has a rocket moving upward with its engines operating. So we draw our rocket ship. The first force we always draw in is the gravitational force. There's no surface in this situation. It's moving upward. It's not on the launch pad anymore. So there's no normal force and there's no friction. There's also no strings, ropes, or cables, so there's no tension force. But there is the applied force from the engines, and that applied force is propelling the rocket upward. So we'll label it as the applied. The last one you had to do was a heavy crate being pushed across a rough surface. So we draw our crate. We then draw in, of course, we've got gravitational force. That's the first force we always draw in. It is on a surface, and so therefore there's a normal force. I'm going to assume that the surface is level, so therefore the normal force acts upward. It is balancing out the gravitational, so I'll draw it as close to the same size as possible. It is a rough surface. There is friction. Let's say that we're pushing this crate. If I draw just kind of like a little picture here. Let's say we're pushing this crate to the right. So therefore the friction acts the opposite direction to the left. It is moving, and so therefore it is kinetic friction. There is no string, rope, or cable, so there's no tension force, but there is a person pushing it, so there is an applied force, and we are applying a force to the right. So again, if we just go down our list each and every time, it'll help us figure out which forces are present, and we draw them as proportional as we can to their sizes. We represent those forces with an arrow because it's a vector. And this will help us then when we solve and start to figure out the amount of each force later on in the chapter.